Hi everyone, and welcome again to Nettle, the go-to place to learn about business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description and click the join button below for more details. My name is Sava, and today we're investigating a quite insightful and ingenious econometric test that can be used to determine whether the regression model suffers from omitted variable bias, whether some variables that should be included in the model theoretically are missing from it, as well as for functional misspecification. For example, if the model is estimated in a linear form and it should be estimated in a polynomial form or logarithmic form or some other version of the same equation. And the test that allows us to perform this quite insightful estimation is called Ramsey RESET test. And today we're going to implement it on an example of our economic growth dataset, where we've got 131 countries and we try to relate GDP per capita growth figures with some well-known macroeconomic aggregates. The logic of the test is to first estimate our baseline regression model as it is, so as normal, and we can do it using the Linus function over here. We can select a 5 rows selection of cells, a 5 rows array with 6 columns, and we've got 5 explanatory variables plus a constant, and we can use the Linus function, selecting the array of our dependent variable values, as well as the matrix of all independent variables, our regressors. Put 1 here for yes, we need a constant in the model, and 1 for additional statistics, and enforce this using Shift-Control-Enter. That spits out the coefficients, the standard errors, and the R-squared. We'll need it later. And we can now estimate the fitted or the predicted value, the expected value of our dependent variable given the regression model, as well as the errors, the residuals. So for the fitted value, we'll need to refer to our constants, and again, a very well-known property of Linus, it returns our coefficients in the reverse order, so the constant is on the rightmost side, and then we just add our first coefficient for log GDP per capita, we multiply it by the value for the first observation, and then we continue as is. So now the coefficient in column E with row locked, as the coefficient stays the same throughout the sample. We multiply it by the value of gross capital formation for the first observation. Then we go to column D for the next coefficient, which corresponds to the foreign direct investment value. Then we go to column C for the inflation coefficient. And then finally we go to column B for the government spending coefficient. And that returns our fitted value of 3.79% as our economic growth figure. And here we can see that we have quite overestimated the economic growth in Algeria. The actual value is minus 1.13%, which means that we can calculate the error, the residual, by subtracting the fitted value from the realized, the observed value, resulting in an error term of minus 4.92%. But what we need to also take into account for the Ramsey RESET test are the squared, cubed, and so on and so forth fitted values. The logic of the test is quite simple. If something is missing from the model, if there are some variables that exist that could explain the dynamics of economic growth, or if the model that we estimate has an improper specification in terms of the functional form, there would be some dependencies that are picked up by squared, cubed, fourth power, and so on, fitted term, and that are not picked up by our independent variables. So the logic here is to estimate an augmented model with fitted values to respective powers, entering our augmented regression. And we will need to test whether the augmented regression with the fitted terms raised to various powers adds explanatory value, explanatory power, with regards to the baseline model. So here we'll opt to use 2 terms, fitted squared and fitted cubed. For obvious reasons, multicollinearity that is, we cannot use just the fitted term to the power of 1. We can only raise it to larger powers, but in terms of the number of those fitted terms, there is no explicit guidance. You could test for one fitted term, fitted squared. You could do two fitted terms, as we do here, fitted squared, fitted cubed, and you can choose to go for more fitted terms. You can add a fourth power fitted term, a fifth power term, and go as long as you please. But here we'll use the simplest non-trivial example with two terms, the squared and the cubed. And implementing this is quite easy. Here we just square the fitted term, and here we cube it. And now we can enforce this formula throughout our sample and proceed to estimating our augmented model from the Ramsey RESET test. So here we select, again, 5 rows for our Linus template and 2 more columns for the coefficients for the fitted terms. And we again use the Linus function, input our dependent variable, which stays the same, that's the GDP per capita growth. And for our independent variables, we also include our fitted squared and fitted cubed terms. Again, if you wish to perform it just for the fitted squared term, you could just stop here, or you could have included more terms, and that would include additional columns where you would have preliminary raise the fitted term to the 4th power, 5th power, and so on and so forth. So the generalization is quite straightforward. However, here we include only 2 terms. We need to add the constant as well, and we do need the additional statistics. And we enforce it again using Shift-Control-Enter, and our regression template appears over here. And what we need to do now is to compare the R² of the augmented model with the fitted terms to the power of 2 to the power of 3 and the baseline R², because we need to test for joint explanatory power added by those 2 terms. And the easiest, the most straightforward, and the most natural way from an econometric point of view of testing it would be the restricted F-test, where we compare the R² of the unrestricted model with extra terms added to the R² of the restricted model, where no additional terms are added into the model. And that allows us to calculate the F-stat and test the significance of this F-stat using an F distribution. That allows us to proceed with the test quite naturally. So in the numerator of our F-statistic, as in any restricted F-test, we would have the improvement in R², which is the R² of the augmented model minus the R² of the baseline model, divided by the number of the additional parameters, additional factors we included. And here we included 2 fitted terms, so we divide by 2. So that's the numerator of our F-stat. It is basically the improvement of R² per additional factor we have included. And in the denominator, we would have the residual of the unexplained variance, which is 1 minus the R² of our augmented model, divided by the number of the degrees of freedom, the number of variability left in the augmented model, which is 123, and it's quite conveniently given by the Linus template over here. In the 4th row, the second term from the left is the degrees of freedom, as it always is in the Linus function. And we can finally enforce this formula, and that would give us an F-stat of 2.38. And now we can test the significance of this F-stat. How likely is that such an improvement, when we included 2 fitted terms, is just due to random chance alone? Again, keep in mind that if you include extra variables in your model, the R² never goes down, it always only goes up. So is this improvement by random chance, or is there something going on there? Are those fitted terms squared and cubed picking up some variability that is left unexplained, and that might be due to improper specification in terms of the functional form, or in terms of the omitted variable bias? Some variables should have been included into the model, but are left behind. And that can be easily done using the right-tailed F distribution. We input our F-statistic first, and then we input our degrees of freedom. The first degrees of freedom value is the number of fitted terms, which would be 2 here. And the second degrees of freedom value are the residual degrees of freedom, which are again quite conveniently reported over here, 123, which is 131, the sample size, minus 8, which is the number of coefficients in the augmented model. We have got the constant, 5 original explanatory variables, and 2 fitted terms. So that all adds up nicely. And then, enforcing this formula, we get a p-value of 9.66%, which is below 10%, but only just, meaning that there is some omitted variable bias potentially in terms of the baseline model. We might have missed some factors that could explain economic growth dynamics but are left behind, or potentially we should have changed the functional form of our model somehow to better model the dynamics of, again, economic growth in these countries. And here is the ingenuity behind the Ramsey RESET test, that it allows to test for some limitations of an econometric model without even knowing what these limitations are. And it is potentially a very good robustness check to carry out for any regression modeling you ever do, just to be on the safe side and be sure that there is no potential omitted variable bias or regression misspecification you could have fall prey to. And that's the Ramsey RESET test in a nutshell and its Excel implementation. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, economics, or finance you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.